The year is 2001, and astronomers around the world are getting ready for what should be a boring conference. The latest data from the Parkes Radio Telescope in Australia has come back, and it est just more of the same old thing, right? Well, one researcher is going to change all of that with the announcement of something completely unexpected. A sudden, incredibly powerful radio signal from deep space. It would have been easy to dismiss this as a one-off fluke, an anomaly in the data caused by static or some other problem with the equipment. But since then, we've seen many more of these mysterious signals, and they're still completely baffling astronomers. So what exactly are they? Are we being visited by an alien intelligence, or is there some other explanation? Fast radio bursts are extremely powerful one-time or repetitive bursts of energy at radio wavelengths that originate billions of light-years away. The first FRB ever discovered was FRB 010021 at a redshift of 1.59, meaning that the galaxy containing the burst is about 18 billion light-years from Earth. That's nearly as far away as we can see into space. It was originally detected in archival data taken years prior with the Parkes Radio Telescope in Australia. As incredible as that discovery was, the real shock came when researchers found that this immense burst of energy had been recorded by other telescopes around the globe only days before, but had gone unnoticed. If the signal had been so brief, just how long did the actual burst last? The original research paper stated that its duration was less than 65 milliseconds, which is nothing in the grand scheme of things, but that's still longer than any other known astronomical phenomenon. To put this into context, a typical neutron-star merger, the kind that produces gamma-ray bursts, happens over the course of days or even weeks. A supernova, the explosion of a star, occurs over several months, but fast radio bursts are over in a flash. The burst of light itself might only last a few milliseconds. But, including the precursor and the afterglow, the entire event is typically no more than a second long. What makes FRBs even stranger is that they appear to come from random locations in the sky. Of course, we know that they don't actually originate where they're seen from on Earth, but rather they're lensed by massive structures in the foreground. That means that a burst from the direction of the constellation Cancer might actually have come from almost anywhere in the northern hemisphere of the sky. But what seems to be random is the fact that the FRBs themselves do unseem to have a discernible pattern. They aren't beamed like pulsars, and it doesn't appear that they're targeted at Earth. Yet their power is immense. When FRB 010021 was first analyzed, it was calculated to have an isotropic equivalent peak luminosity of 10 to the 37th ergs per second, which is about 2 orders of magnitude more energetic than the most luminous gamma-ray burst ever detected. However, we now know that the burst didn't happen in an empty patch of space. It was within a massive galaxy that hosted hundreds of billions of stars. And this has led some astronomers to suggest that the true luminosity of the burst was much higher, perhaps as much as 10 to the 40th ergs per second. To put that into perspective, it's about 10 times more powerful than the Big Bang. If that sounds unreal, get ready for FRB 121002, which has been detected multiple times and has an even higher estimated luminosity of 10 to the 41st ERGs per second. It comes from a dwarf galaxy that's 3 billion light years from Earth and has been nicknamed the Fast Radio Telescope FRB. So if they're so incredibly powerful and come from relatively nearby, why haven't we been affected by them? Well, for one thing, the bursts only emit radio waves, whereas most other extragalactic transients also emit gamma rays and X-rays. In addition, the bursts are very short, meaning they don't do more than briefly bathe the surrounding universe in radiation. Finally, the bursts don't appear to be aimed at us, while they're coming from relatively close by in astronomical terms. They're still very distant, and the radiation has spread out over a huge solid angle. If they were more focused, they could certainly be dangerous. But as it is, they're harmless. While the exact mechanism behind FRBs is still unknown, astronomers have been able to learn a lot about their properties through extensive follow-up. Observations of previously detected bursts. We now know that most of them occur in galaxies, and they often produce not only radio waves, but also X-rays and sometimes optical light too. They've also been found to be variable, with some repeating with high periodicity, while others don't seem to repeat at all. One example of a highly periodic FRB is FRB 121002, which has been observed to repeat every 157 days, like clockwork. Another example is FRB 171012, which exhibits an even higher level of periodicity, with pulses occurring every 16 days. These pulses typically last only a few hours, but they continue to emit radio waves even when they're not actively bursting. This suggests that there's a central engine powering the burst activity, and it's constantly emitting radiation. But the bursts are only detected when the beam is pointed towards us. However, not all FRBs are so predictable. Some, such as FRB 190520, repeat with different timescales, suggesting that they're not associated with a single compact object like a neutron star. Instead, it could be a binary system with both objects contributing to the burst emission. Other FRBO 20124 repeat in a way that suggests that the bursts are being generated by a magnetar, a type of neutron star with an extremely powerful magnetic field. So, what could be causing these strange bursts of radiation? Well, it's possible that they're produced by the collapse of a massive star, a process that we know can generate powerful explosions called supernovas. However, this doesn't explain the periodicity that some of the FRBs exhibit. Others have suggested that FRBs might be produced by a type of neutron star merger that doesn't produce gravitational waves. But again, this doesn't account for the wide range of different behaviors that have been observed. Some researchers have even suggested that FRBs might be produced by aliens. either as a side effect of their industrial activity or intentionally as part of a search for extraterrestrial intelligence. While this may sound like a far-fetched idea, it's actually not as crazy as it might seem. After all, humanity itself produces radio waves that can travel to other planets and potentially be detected by alien civilizations. And who's to say that aliens wouldn't do the same thing? In 2020, scientists reported the detection of a fast radio burst that had been repeated over a period of 47 days. The burst originated from a galaxy that's about 1.4 billion light-years from Earth, and it was significant because it showed clear signs of evolution during the 47-day period. The burst rate increased until day 33 and then decreased until the end of the observation period. This suggests that the FRB source may be intrinsically variable, or that it was affected by the interstellar medium of the host galaxy. Another study published in 2020 used the Very Large Array to image a fast radio burst source in unprecedented detail. The study focused on FRB 121002, which had been previously detected by the Arecibo Observatory. The new observations revealed that the burst source was located in a heavily lensed region of space and that it was extended over an area of about 11,000 light-years. This finding provided insights into the physical properties of the burst source and the nature of the lensing galaxy. More recently, scientists have used the Fast Radio Telescope to make the most precise measurements yet of an FRB source. The study focused on FRB 121002 and used a technique called dispersion-based flux density measurements to determine the burst source S position and size. The results revealed that the source is located in the center of a dwarf galaxy and that it spans an area of about 210,000 light-years. The study also found that the burst source is highly variable, changing in brightness by up to a factor of 10 within a single day. In addition to the studies mentioned above, scientists have also made significant progress in understanding the origin of fast radio bursts. One leading hypothesis is that FRBs are produced by magnetars, which are neutron stars with extremely strong magnetic fields. Observations of FRB 121000 to have provided evidence in support of this hypothesis, showing that the burst source is associated with a highly magnetized environment. Another theory is that FRBs are produced by binary systems consisting of a neutron star and a white dwarf or two neutron stars. These systems can undergo a process called a Roche lobe overflow, which could potentially generate the observed burst of radiation. The future of fast radio burst research is bright, with new telescopes such as the Square Kilometre Array and the next generation Very Large Array set to come online in the coming years. These instruments will provide unprecedented sensitivity and resolution, allowing scientists to probe the nature of FRBs in greater detail than ever before. With continued observations and theoretical work, we can expect to make significant progress in unraveling the mysteries of these fascinating phenomena. What do you think? Is there anything we missed? Let us know in the comments below. As always, don't forget to subscribe and we'll see you next time.